Welcome to this session. My name is Marius. I am a PhD student here in the Berlin Mobile Brain Body Imaging Lab. And for some weird reason in the last years, I have developed a genuine passion of squeezing as much juicy data out of our very noisy data that we collected. So that led to the MoBI pipeline being developed a few years ago, actually in the beginning. And yeah, you've already seen the beginning parts of this, which was the import developed by Sane. And today, or in this session, I will be speaking about the Eeg Pre-Processing. So this is the part that we are discussing in this session. Actually, it's kind of part of a larger session which contains pre-processing and ICA. So there will be the lunch break in between. Depending on the time, it could be that the lunch break is cut into the pre-processing, but this session is actually more one than two and should be taken as such. Okay, so if we zoom in here into the pre-processing, this is what we are going to do in this session. And that's going to be an overview of the MoBI pipeline complete Eeg pre-processing steps. The pipeline itself comes with wrapper functions and all. I will not discuss these right now, but in the end, because if you run them, it will block your PC for a few hours or days. So we'll come to that. Here, this is the release. Yeah, Sane has already broken the ice. I think you all know that we need this code in MATLAB integrated in EEG Lab. But in addition to that, we also need the data and scripts specific to the session, and these are available on the Google Drive folder, which is marked in blue here. The data, the actual data that you need to follow along is just this little hands-on pre-processed ICA. It's around 80 megabytes, so even if you didn't download it so far, you can still do so. And the script you need to follow along with this session is this one, also the hands-on script. And these, the MoBI config script and the example MoBI pipeline, as well as the two raw EEG Lab folder, these are only necessary if you want to run the complete pipeline, which, as I said, I don't recommend doing just now. It's going to be at least a few hours, even on a good PC. Okay. So with that being said, this already said. So with that being said, I want to start with a little poll, and I will try to use more polls throughout the session. Give me 1 second to add this here, because it is very interesting how everyone treats EEG data differently, and how different labs and different people have different approaches. So let me just start this poll, and it's there now. So you can enter your opinions there, and I will give you a few minutes or so to get started and get everyone involved who wants to. And I'm actually really interested in what is going to be the result. It already looks like we do have many people that have scripts where they only adapt parameters. That's really cool. That means that you already have plenty of things in order, which is great to know, actually. A little spoiler alert: the pipeline is going to be the same thing. It's going to be number 3. It's a script toolbox, basically. I mean, you already know it, which has this config file, and you are basically supposed to only change the config file, and you don't need to add new scripts if you want to follow along the exact pipeline, obviously. All right, very cool. We have a clear winner, number 3. I have a script base where I only adapt parameters, and the others, the GUI and new scripts every time, and random methods from the internet are about the same at around 3 or 4. Very cool. Thank you for answering this. That's very cool. And now we can continue to the actual content. So we start with this, the removal of non-experiment segments. Now, why is this important? So this is a plot, one of the data sets that we have in the hands-on session or in the raw EEG lab folder. I think it's 64 if you want to plot it yourselves. And you can see this is the complete session, right? You can see kind of the first part. There's a little bit more data noise here, a little bit cleaner on the right side, but there are these crazy artifacts in the meantime. Okay, so this is, as I said, the complete, like an hour of data or something. Now, if we look into this data set, we find event markers, which denote the beginning in green and the end in red of specific sessions. So here we have baselines, then the walk, 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 walk condition, another baseline at the end, another baseline for the next block for the larger part, and that's the stand, 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 stand conditions, and then the final baseline.
Just a quick question. Can you use the laser pointer to...
Sure. Yeah.
Thank you.
Thank you for reminding. Yes. And here, yeah, the second baseline. So the stuff in between, that's actually not so great, right? This is the time slot pre-experiment. Then we have the breaks, lots of breaks, and you can see that the large artifacts, or some of the very large artifacts, are in the breaks. And that's not necessary. We don't need to analyze that. So we just remove this. And if you imagine the gray areas not being in your data set, that looks already much better. Of course, this is specific to each experiment. There is no pre-created script for this. So this is something that's actually one of the only things that you do need to script for every experiment. And you also need to script it yourselves. You just need to do it right after you loaded your data. Okay, next part, and that is Zapline. Zapline is a pretty new method developed by Alain de Chevenier, published only last year, which is, as the title said, a simple and effective method to remove power line artifacts. There is really not much to add to this title. It's just true. So here is a plot where you can see on the left side, that is the spectrum in the beginning. Then we can see here at the line frequency, which is here the bottom axis is relative to line. So so 1 is 50 Hertz, and you can see there's a large spike at 50 Hertz and another large spike at 100 Hertz, which is the harmonics. And if we run Zapline with 50 Hertz removal target frequency, we see that it really removes this large spike and nothing else, which is great. You can see a few others there, spikes there in addition, but I'll come to that. So how does this work in principle? We have first a split of the data in 2 parts. So basically what's happening is we filter the data once with a notch filter, which is which just basically kills the complete spectral part of 50 Hertz and harmonics. So there's nothing remotely line noise left in this part. That's the clean data part. And once we filter with the inverse of that filter, which is the exact opposite. So it's the noisy part only, but it's not only the actual line noise, it also contains the little regular 50 Hertz part that is just in the EEG data, right? So, but that's 2 parts. If we just add these two parts together, we have the original data again, because it's filtered with the exact inverse. Now, the next step is that a spatial decomposition is used to remove noise components from the noisy data part. So it's, if you will, in some way similar to a principal component analysis or a independent component analysis, which will be in the next session. But in the end, it just removes a spatial filter or spatial component from the data. And that is supposed to remove only the noisy components, the most noisy components. And then the now cleaned noisy data is added back to the already clean data. And that means that we have this nice green spectrum there. And the advantage here to notch filters is that it's giving you the full spectrum. You don't see the notch, right, that you would have otherwise if there was a notch filter. And it's very important to do that, actually. There is physiological activity in the 50 Hertz range, and some experiments could not be done if you wanted to use a notch, or if you would use a notch filter. You would just get no results. And another option would be, for example, to just leave everything in and hope that ICA can catch the noise and remove it. But the advantage of Zapline, as opposed to ICA, is that the data actually remains full rank, and it will potentially lead to a better ICA decomposition. So and that's something that I want to test in the future. This is anecdotal evidence, let's say. I think it improves the ICA decomposition, and yeah, I will have a look at that later. Okay, so a little bit more about Zapline. There are some problems. So first of all, you do need to specify the number of removed noise components. In the original paper, 1 to 3 component removal is recommended. The default is just 1, so only the first noise component is removed by default. In our data in practice, we did find that 1 or 1 to 3 was definitely not sufficient, more in the range of 10 around that. And another part, and this is probably linked to the first issue here, that it assumes stationarity. So since it uses a spatial filter, it assumes stationarity throughout the entire experiment. So, but the spatial distribution of line noise can change, especially in MoBI experiments where you touch cables every now and then. You, of course, change your orientation, and depending on how the line noise is like zooming around through your lab, this will also change stuff. You can have other mobile line noise sources, like you carry something around and you move it like closer to your head or further away and so on. So this stationarity assumption is definitely not a given in our mobile brain body imaging experiments. And the last part is there is a slight potential of overfitting, especially with very high density EEG. If you have 128 or more channels, it's possible that the spatial decomposition is problematic, and a PCA reduction before using Zapline is potentially necessary. So this part is implemented in Zapline, but by default, it's not used. So there's a little extra code repository called Zapline Plus, which is basically a bunch of little improvements and wrappers to the Zapline functions. The first and most important part is that it automatically detects the number of components to remove based on the badness of the components. I'll show some plots later. And it chunks the data into segments to account for these non-stationarities. So it uses Zapline only on small data segments. And there's also an automatic rank reduction, which is dependent on the number of channels to prevent the potential overfitting. This is available online on GitHub here at my repository, Zapline Plus. So the Here I will show a little example of a data set that is the actual hands-on data. I will show you later which code lines you need to run to do it, but maybe if you have it open, you already see it. It's all there already. So this is some raw data parts, and if you run Zapline, the first iteration of Zapline, I want to remove 50 Hertz. That's the spectrum you already saw. But actually, we see that there is still some noise present, right? And it's at different frequencies. So we are not quite sure about all these noise components, where they come from, but they are definitely there. So what we do is we just use Zapline again with a new iteration where we use this data and clean it again. And in this case, with 21 Hertz, you can see this is this part, and you can also see that it removes a lot. And it works very nicely. We have a suspicion that this 21 Hertz component is coming from the phase space tracking system. Yeah, but this is just something that we observed. Something that you can see in addition here in these plots is here in the top plot, the x-axis is the chunk. In this case, it's 30-second chunks. And you can see the data has 20 chunks, so it's rather short. It's just, I think, 10 minutes, 2 times 5 minutes standing and walking. And you can see that the automatic removal of components is going up and down depending, with the chunks. So with this 21 Hertz components, for example, in the second part, there isn't so much anymore. And here you can see the mean artifact scores. That's like the badness of the components that are removed. And you can see the red line where the algorithm cut and said, this is noise, this should go out. And there's one last iteration here at around 89.35 Hertz. And 89.35 Hertz happens to be just below the refresh rate of the virtual reality head-mounted display, which likely means that this is the head-mounted display, just the frame rate wasn't quite up to 90 Hertz. Sometimes it dropped the frame or something like that. So, but this also can be removed. It's not perfect. You can still see some bumps and so on, but we can also remove that using Zapline. I am reading the question by Arthur. Does removing 21 Hertz component not distort the brain signal? It is, of course, let's say it's unlikely given the algorithm of Zapline. Of course, we can never be 100% sure about that. I'm in the process of investigating the Zapline thing a little further, and potentially that's going to be, the Zapline Plus is going to be one of my next papers. And I know other people who are using Zapline in the 50 Hertz range, actually, so in the gamma range, and they cannot do their experiment without Zapline, basically, and they get reasonable brain signal after removing the data with the noise with Zapline, and not without doing that, because Zapline only removes the bad components in the noisy data. So anything that is not notch filtered, which is likely not EEG data, is not in that part. So yeah, let's just say you can never be absolutely sure, but I think this is pretty fine, especially if you look at the spectrum here. Okay, so in the end, after you have Zapline done, you can see the clean data here. Especially this one channel has apparently lots of line noise, and you can see it's gone here. The channel is likely still bad. I mean, this is probably a bad channel in the first place, but also other channels do look cleaner, and in general, the difference isn't huge. It's not magic, but it's just one of the little things that might improve your signal strength in the end. And here you can see again the spectrum of the beginning and the spectrum of the end. So to wrap it up, is it perfect now? Of course, it is not perfect. Sometimes Zapline just cannot remove some artifacts. I haven't found out why. Sometimes, no matter how stringent you make it, you just can't remove stuff. But yeah, that's just what it is. It's always important to look at this plot in the end and decide whether everything is okay. But in general, it's working quite nicely. And there's one last thing to look at, and that is what happens when there is no noise in the data in the first place, right? Does Zapline distort data if it is applied in frequencies where there is no such peak? And the answer is no. It literally doesn't do anything. Even if it removes, like, sometimes one component, in rare instances even more, the spectrum isn't distorted at all. You basically cannot see any change. So that's reassuring. Okay, so now we do have the hands-on session. You should have this MoBI workshop hands-on preprocess ICA script. And in line 24, you can see the segment which removes line noise with Zapline. I have stopped the time on my PC at home. It takes 2 minutes. On my old little notebook, it takes 4 minutes. So that's the range you need to calculate with. Yeah, that's just how long it takes. This is a 10-minute data set. Yeah. One thing, don't forget to adapt the file path. So in the script, you need here in this file path, line 22, you need to adapt it to point to the actual data folder where you downloaded the data to, and then everything should work. And then you should have this EEG raw data there. So now you can test a bit, and you may want to use different thresholds or other parameters. They are all commented in the script. I will be watching the Discord chat and give you a few minutes. And in the meantime, I will have another poll for you to fill out. And this is coming right now. No. Like this. Wonderful. So here you can tell me how you usually remove line noise from your data so far. I am also very, very curious what you think of Zapline now after you've seen it here, or whether you have tried it already someday. And yeah, as I said, I'll be watching the chat for a few minutes. So this is like a little break. It's half an hour after I started, so that's nice anyways. And you can play around a little bit with it, and I'll be watching the chat. Marco, I do think that might mean that your Zapline is not installed. Did you get an error message in your when it started, like another error message? So this is not a standalone feature of the MoBI pipeline. It does require the Zapline noise tool, or the noise tools toolbox by Anand de Chevigny. You can download it on his server. It's not standalone on the MoBI pipeline. So that's important. And you should also definitely cite the paper, obviously, if you use it. It's not made by me. It's an algorithm by Anand de Chevigny. So looking at the poll, we already see that most of the viewers here use a notch filter so far, and some have used Zapline. Some, oh no, my poll didn't work out. I wanted to know how many of you have clean data.
I take 6. I have boring clean data all the time.
Yeah, that's because you don't look at it.
No, definitely not.
Oh no, I want to change this. Yes.
I think it's okay with the poll. There's
Yeah, I
another
know.
question.
Just wanted to know, maybe someone wants to add something. Okay, so I hope it's working for everyone, and maybe I can let this run in the background.
Yeah, there are meanwhile more questions in the chat
Yes.
regarding the Zapline approach. Maybe you can again explain how Zapline exactly removes the specified frequencies.
Yeah, so why does Zapline remove the component in the notch filter data and not in the full spectrum data? Because it's easy to identify the noise components this way, but are there potential problems when recombining the two sets later? So as far as I know, there are no problems when recombining them. It literally, if you just recombine them after like doing the filter and filter with the inverse, there would be no change. But in theory, I mean, there is always some mathematical imprecision, of course, but it should be negligible in range. And why does it on the notch filter data? So it's doing it on the inverse of the notch filter data, not on the notch filtered. So the notch filter is the clean part, which is, let's say, the default. So if you remove all components of Zapline, you will get notch filtered data. It's that's very simple. So that's, let's say, that's the worst case if you want to do that. But oh yeah, you were thinking of filter artifacts. I mean, let's say I didn't write the algorithm, of course. This is a question that I would like to pass on to Alain de Chevenier, but I don't think so. I mean, essentially, it is. Sorry. So I don't think there are filter artifacts because it is a spatial filter in the end. I mean, the notch filter is always a notch filter, right? And it doesn't actually really apply the notch filter in that sense, but of course it could be. By default, Zapline uses a filter which has a relatively wide roll-off, so it's not super notchy. It's actually more of a bouncy thingy. And not an actual like really V-like valley. So I think that was also done in order to reduce any kind of filtering artifacts. And yeah, I think that's all I can say about that. I didn't see any so far. Everything worked very well with Zapline, and the way I understood the algorithm, it's very well crafted and thought through with these kind of things.
Yeah, thanks for the explanation. I
Yeah.
don't know, I should look at the paper if I want more.
Yeah. So one person has no person, only the bot has clean data. Yeah, I thought so. Okay. Filter the data at low pass at 30 Hertz, so Zapline line noise is not an issue. Yes, Berlin, that's definitely an option. In that case, you, as Eeg has pointed out, yeah, this is not a great approach if you want to do MoBI analysis because all the muscle information is lost in that case, but it still contaminates your data in the low frequency. So yeah. Okay, let's continue. And that is the next part, adding the reference with zeros. This is not mandatory, just like the removal of non-experiment segments isn't mandatory. It is recommended in some circumstances, and the question is, why do we potentially do that or want to do that? So have a look at this channel location plot here. So these are the channel locations, for example, in the data, the hands-on data in the raw EEG lab that you could download. And these are the locations here, and the reference actually was in this channel. So that's the FCZ reference. But since the reference is used as a reference, so the FCZ, it cannot be used for anything else at this point. And that's because the channel voltage, if you load it in MATLAB, is essentially just the difference between the voltage at one electrode minus the voltage at the reference. So the reference is essentially just a channel full of zeros. So it still exists, but it doesn't have any data, if you will. It's just zeros. Now, when you re-reference, the original information can be retained. So when you re-reference, for example, to the average reference, you can still like feed back the information of this channel. If you, for example, want to analyze the EEG at that location, obviously that's useful then. And also for later, for the next session here, if you want to do an ICA and you want to keep the full rank, then this is also helpful, because otherwise, if you compute the average reference, you lose one rank in your data matrix. I'll come to that. Yeah. So adding the channel logs, this is mandatory. It also kind of makes sense, because otherwise you couldn't do these plots and these topographies later from ICA. I'm keeping foreshadowing to the next session here. This is, in this case, you see the names here. These are just standard 1020 locations. In that case, you don't really need to add anything. It's by default added. So if you don't provide any location file, then it just looks up the dictionary for these names and gives them the appropriate standard location. But it's also possible to have individual electrode locations. So, for example, in our cases, we often record data with an equidistant layout. So the electrodes are not in the 1020 system in our cases, or in many of our cases, but they are in an equidistant layout. So there is no standard location for that. We do need to record our own locations. For example, with this ET guy here, where you really have to point at every location and press a button. Okay, this is electrode green 1, green 2, green 3, and so on. Takes a while, and it's a little bit prone to human error, but of course, if everything works, it's better than using just standard location, because it's just more suited to the skull of the participant in this case. It would be even better if we had individual MRI scans, but I'm going to skip that for this session. Okay. And now we have these channel locations added, and the pipeline will give you this basic prepared eeg.set file, right? So you cannot see that in the downloads, but if you run the pipeline with the wrapper that is provided, you will get all these. It's too much data, that's why you cannot download it. It's just would take too long. And you would get this kind of folder structure where you have, for every participant, you see this Eeg Pre-Processing folder right there. And then you can see the basic prepared set. That's everything that happened until there. And you can also see some analytics plot of Zapline. That's the stuff that you already saw. And the other plots will follow suit in the next part here. So this is the current status. And here we go to the next part, very important, especially in MoBI detecting and interpreting bad channels. Why is this so important? If we look at our data, we do see that some channels just don't behave like actual EEG channels. And this is even more likely in MoBI data where, for example, individual locations might not fully attach to the skin because you move your head, or a cable regularly touches some electrical thing and is breaking, and so on. So it can happen in MoBI data quite often that you have broken channels, and we want to remove them. I guess this is not news if you already have been working with MoBI data, but I want to go a little bit more into details on how we do it. But yeah, first of all, obviously, if you want to compute ERPs or ERSPs or any other measure that you want on this particular channel, you can't, because it doesn't give you any real data here, because it's broken. And also, foreshadowing again to the next session, the ICA decomposition with these bad channels is potentially worse. It's not necessarily worse. ICA is pretty powerful, actually, but removing and interpreting bad channels can help. Importantly, just as a side note here, if you remove channels and interpolate them, you will have to reduce the rank in the ICA algorithm. Again, I'll come to that, just didn't want to ignore it here. Okay, so How do we do it? This is a subject of debate, also here in the lab. On the one hand, you have the manual detection, right? Manual detection means it's exactly as you want it. If you think a channel is broken, you can remove it, no matter what. you just select what you don't like. It's like let's say it might be exactly as you wanted, but it's a little bit subjective, right? So it's always a person that looks at the data, and it's a little tedious. It takes time. And in rare cases, it's difficult to argue, also to argue why you chose this and not an automatic algorithm, for example, depending on who reviews your paper. So just all in all, it's potentially unreliable, but I want to emphasize that it is still exactly as you want it, and if you have experience, it might be the best solution available. It's just not automatic. So in the pipeline, it's not used. In the pipeline, we use something else, and that is Eeg Lab's clean artifact function. This function is part of the clean raw data plugin. It is the same algorithm as in the prep pipeline. I believe it has been developed by Christian Cote, great programmer. He also coded LSL and a bunch of other toolboxes that we use. Really cool. The prep pipeline is the clean raw data Eeg Lab plugin itself doesn't have a paper, but it's the same algorithm underlying here, right? So the great boon of this method is that it is automatic, right? So you just run it and it gives you some data that is, or some channels that it rejects. It is objective in the sense that you have an algorithm that's doing it. It's not a person, and it's replicable in principle, and it's easy to defend usually in your paper, for example, and because you can just say, well, I did it with this algorithm. It's published. Okay. A bit of an issue is that you may disagree with the outcome, right? So maybe you just know that this channel is bad, and the algorithm just keeps not detecting this channel as bad. We do have such an example even in this example data set. And this is a problem, right? It's a trade-off, always a trade-off. You might want to change a few parameters here and there. But the idea, obviously, of using this is to not fiddle around with the parameters until the channels you want to remove are removed, but to just let the algorithm do its thing. And this comes at the cost that you might not always like it exactly as it is. Looking at these criterions in the algorithm, we do have a bunch of unused criterions. This is also what happens to show up when you're opening the clean raw data in the GUI. And the first that we don't use is the burst criterion. The talk yesterday by Zara already mentioned this. This uses artifact subspace reconstruction to remove artifacts. This is potentially very beneficial. I mean, the evidence is convincing, but it's also a little bit tricky to select the baseline data in MoBI. That's why I asked this question yesterday too. In my experience, the automatic detection fails completely and horribly. It doesn't work at all. In MoBI, it works quite okay in stationary data, but not in our case. And that's just not great. Or I do think that it can distort the data. It can distort the data to a degree that I don't want to trust it in a fully automatic pipeline, at least not now at this point. And that's why this is unused. And another thing that's unused is the window criterion, and that just removes samples, which we don't want to do at this point, and actually not at all. But I'll come to that. So the criterions that we do use actually in this toolbox, that is first of all the high pass band. So this is a filter that removes slow drifts. That's just necessary for the channel removal detection to work. The problem is that it does distort ERPs, so it should not remain in the data. So that the data should not remain filtered like that. It should just use the filter to detect the bad channels. And that's how we do it. So there's a wrapper function that uses this toolbox, and it's only used for the detection with the default parameters of filtering from 2.5 to 7.5 hertz. And that means a cutoff of 0.5, which is just default. And there's another criterion, it's called the flat line criterion, which basically determines the maximum duration a channel can be flat, so not showing any signal, in seconds. And the problem with MoBI data is this can happen, right? It can happen even between blocks. So in breaks, it can definitely happen if the participant moves out of the room, for example. But breaks are to be removed in this part here, right? So that should not be that big of an issue, but this can also happen between trials. So even if you don't have an explicit break between trials, sometimes things happen and the participant goes out of the room and signal is lost or some other things happen. And you as a researcher, you just continue, you maybe restart the block, but actually the break, there was no break signal. So these flat channels are in the data you have, and that means this channel will be removed. By default, this is switched off. And I do think this is not much of a problem because the later to be discussed criterion that we do use is working just fine usually. Another thing is the line criterion, which is basically trying to remove channels that still contain excessive line noise. The problem is that it defines, for example, line noise channels by having a standard deviation that differs from the total channel population, or having, just it determines line noisiness by looking at the other channels. And the problem is that in MoBI, you maybe have channels here at the neck or at the back of the head, not exactly around the neck, but the back of the head, for example. And these kind of channels are sometimes just detected as line noise channels, which they are not. They contain muscle activity. So that's why this is also by default switched off, but it's possible to switch it on in the pipeline if you want to. Okay. Now, what are actually the criterions that we do use in this algorithm? And that's two basically most important criterions, or basically it's just one, which is the channel correlation criterion. This means the channels are, every single channel is interpolated using a random sample of other channels around this channel. And then the channel is correlated with its own interpolation. And if the correlation of the channel with its own interpolation is less than a value, which is this criterion, then the channel is considered bad in the time window where this correlation did happen. So the reasonable range for this is something in around 0.8, 0.75 to 0.85. 0.85 is rather strict, and 0.75 is rather lax. So yeah, by default, it's 0.8, and this is also the default in both the pipeline and the actual toolbox. And there's one last thing here, and that's the channel criterion max bad time. I've already mentioned this here. This channel correlation is done in given time windows. So this is a few seconds of data where this correlation happens. And then in this time window, the channel is considered as problematic. And then you have this additional criterion here, which says, okay, how often can this happen? What's the fraction, the maximum fraction of the data where a channel can be problematic? And then we still don't remove it because maybe you just deal with it and think it's fine. And this can be either in seconds, if it's above 1, or in a fraction that's like below 1, or 0 to 1, if you will. and this is reasonably in the range of 0.1 to 0.6. 0.1 is rather aggressive. That means that a channel can only be, a channel must work perfectly or like must be above this threshold in 90% of the time, whereas 0.6 means only 40% or yeah, it's enough for the channel to be considered okay. So this is something that you also want to look at probably if you look at this algorithm.